Hey everyone, welcome back, and today let's solve Leetcode problem 2579, count total number of colored cells. So there exists an infinitely large two-dimensional grid of uncolored unit cells, and we're given a positive integer n, which indicates that we must do the following routine or operation for exactly n minutes. At the very first minute, we color any arbitrary unit cell blue, and every minute thereafter, which basically means every minute after that unit, and correspondingly after each one, we have to color blue every uncolored cell that touches a blue cell. Basically, all the cells that are four-directionally adjacent to every blue cell. And below is a pictorial representation of the state of the grid after minutes 1, 2, and 3, kind of just simulating what would happen and how many cells and which cells would be painted blue, basically colored after 3 minutes of painting. In the first minute, we'd just be coloring that singular unit cell, so we'd have 1. And in the second minute, we have 4 extra, so we get to 5. And in the third minute, we'd be painting the 4 adjacent cells for each of those cells. And so we'd get a total of, I believe that's going to be 13. Right? And we want to simply return the number of colored cells at the end of n minutes. So in example 1, we have n to be 1. At the end of 1 minute, of course, we're only going to color exactly one blue cell, like the problem statement tells us. And so our output is 1, because we only have one colored cell at the end of 1 minute. In example 2, we have n to be 2, and like the problem or visualization also tells us, we'd have 5 blue cells or 5 colored cells painted after 2 minutes, right? There would be the 4 colored cells on the boundary that we paint in time 2 or minute 2, and then the 1 original blue cell that we painted in the center in the first minute, and so we'd have a total of 5 as our output. So for the constraints here, we see that our input n integer, basically the number of minutes, is not going to exceed 10 to the 5th power, and is always going to be non-zero and non-negative, basically meaning it's going to be at least 1. And that leads us to the main observation that we really have to make to really solve this problem. Right? Not to overthink this problem as a whole, it really is just a straightforward math problem where you really have to identify the math of how this pattern and how the number of colored cells actually grows in a specific pattern as the minutes increase, right? And that's the main kind of key takeaway that you have to really understand from how these how the pattern really works of how these blue cells are increasing and how many are actually being painted, right? So that kind of leads us to the main thing, right? Colored cells evolve over time. Of course, as minutes grow larger, the number of colored cells grow larger, right? Minute 1, we only have the initial cell to be colored. Minute 2, that initial cell plus its 4 adjacent cells, up, down, left, and right, would be colored. That would be 5. Minute 3, we just expand that pattern forward. We'd add cells or color cells around the existing ones, and that really kind of leads us to that observation where that the colored cells is going to actually form a diamond shape, and it's always going to expand outward as we color more cells that are four-directionally adjacent with one another outward each minute, right? Like we saw in this example. First it's like this, then we kind of get that diamond shape to form at the third minute, and even in the second minute, if you will, as well, right? So basically, really what that means is that the number of new cells that we add each minute after the first would actually form an arithmetic sequence. So we go from 4 to 8 to 12. It's kind of like a very good math problem or pattern to know, right? An arithmetic sequence on a high level basically is when we have a constant difference between consecutive terms. 4, 8, and 12. 4 minus 8 or 8 minus 4 are 4. 12 minus 8 is 4. The difference between every single element that is adjacent to each other is going to be exactly 4, right? So that kind of brings us to that kind of formula that we really need to go with. And of course, I have to include an etc. here because this is technically infinite. Right, that kind of leads us to the main formula. The total number of colored cells after exactly n minutes really can just be derived from the sum of the first n odd numbers, and that would basically just be n squared. And also, the previous layers would still contribute more colored cells, specifically n minus 1 squared cells, right? And so if we combine these as a whole, basically the total number of colored cells after n minutes, regardless of what that n is for our input, would be n squared plus n minus 1 squared. To reiterate how we get those, basically, to get the total number of colored cells after n minutes, that would basically just be derived from the sum of the first n odd numbers, like we saw in that pattern, so that would be n squared, and then the previous layers that we already painted in previous minutes would be n minus 1 whole squared cells. And so the total number of colored cells after exactly n minutes, that would be our main formula here, would be equal to n squared plus n minus 1 squared. So that's my parenthesis. whole squared, right? So now let's go ahead and see how that's actually implemented in code. It really isn't too bad code-wise. It's really thinking of that formula and analyzing that pattern to really get that desired solution for each input n, right? So first, like we talked about the first part of our formula, we want to know what n squared is. And so let's actually compute that value based on our input n. The current layer, basically the current minute that we're adding at in the current minute n, it's going to be n times n, or basically just n squared, right? That's going to be the number of cells that we're adding in the current minute or in the current layer of our diamond shape of blue colored cells, and that would be n squared. And so we'd simply just store it, or store that square value in this current layer integer. Then we have to compute the second part of the total number of blue colored cells after all n minutes of painting blue colored cells. That would be n minus 1 whole squared. So let's compute that value as well, right? So basically computing it, the previous layers, how they contribute to the total number of blue cells as a whole, not just on the current layer, but as a whole, kind of like the sum would be n minus 1 times n minus 1, or just n minus 1 whole squared. Either one really works, right? This is basically the number of cells in all the previous layers combined, not including the current layer or current minute that we're painting. That would be n minus 1 squared, and we're storing it in this corresponding variable. Now, what does the problem statement literally tell us to do? Well, it literally tells us that it's going to be this n squared, basically the current layer's number of blue colored cells, plus the previous all layers blue colored cells. And so we want to return the sum. So I'm going to do it a little bit more formally. I'm going to get the total cells, or total colors, I'll just say cells. That's going to be the current layer, how many ever balls we're painting, or cells we're painting in the current layer, plus the previous layers. How many cells we painted as a whole in all the previous layers. And effectively, we want to return the total cells, regardless of, depending on whatever it is, based on the input, right? Basically, we're just adding the current layer and the previous layers to get the total number of colored cells throughout all the layers after all the n minutes as a whole entirely, as kind of like a sum. And effectively, we're simply returning that value. That would be the computed total number of current cells or colored cells for the entire input n, for after all n minutes, or all n operations on all the layers that we paint them for. So if we were to, okay, let's see what I did wrong here. Yeah, so I forgot to say previous layers. Sorry about that, guys. Quick syntax error, rather logic error on my part, and naming my variables. Now they should actually work. And as you can see, really this is just about as efficient as you can get, both runtime and memory-wise, right? So let's kind of get into how this code works as a whole on a high-level rundown. How is our code actually working? Basically, it's really just kind of the main idea is actually recognizing that colored cells, the number of blue colored cells that we're painting, it's going to expand symmetrically, again, forming that diamond shape of patterns that we paint blue cells in. Really, so instead of actually simulating each step, kind of like a DFS or something like that, we can use a formula to actually compute the total number of colored cells after any number of n minutes for any input directly, right? That would be that main formula where we'd get n squared plus n minus 1 whole squared, right? It would be the total count of all the blue colored cells for after each minute, or after all n minutes. It would be the sum of the two squares, n squared for the current layer and n minus 1 whole squared for all the previous layers blue colors that we did. And that would be a very efficient solution as well, kind of bringing us to the runtime complexity. The runtime complexity of this is actually going to be a big O of 1, or constant runtime complexity. Why? Because we're really just performing a constant number of operations regardless of the input size, with just these squares and addition operations. So this would be a big O of 1, or constant runtime complexity. And very similarly, the memory or space complexity is also a big O of 1, because we're not actually using any auxiliary memory or any extra data structures. We're actually using a fixed or constant amount of space for the variables, like you see with these integer variables, current layer and previous layers. And so this would also be a big O of 1, or constant time, space, or memory complexity, right? So really the main part of this problem is actually leveraging the mathematical insights to actually compute the result directly, and avoiding any iterative or recursive process or simulation, just using this formula as a whole, right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.